Try to make it a little bit larger here. All right, so but as I was saying there, right, so when we have this number 505, okay, the 0 is a placeholder. But if you didn't have that, instead of having 505, you would just have 55, right? So that placeholder is actually very important. So when we look at every single numbering system that we have, we're going to have one of those values is going to be the 0. It's critical. So, you know, when we add up numbers and things, all right, we basically have these places. We have the ones place, the tens place, the hundreds, the thousands, the 10,000s, and so on. Okay, and so we don't normally think about it, but like if we were to come back here to this 505 number, for instance, what we're really saying here is that we have 5 times 100 plus 0 times 10 plus 5 times 1, right? So when we say we have 505, this is what we're saying. We have 5 times 100 plus 0 times 10 plus 5 times 1, of course, gives us 505. Now this here subscript indicates base 10. Okay, so you see the little subscript that we put on there indicates that we are in the decimal system or the base 10 system. So the thing is that computers can't distinguish 10 different values in the same place. All right, the way a computer looks at things is it's either got a high voltage or a low voltage. We kind of talked about that with digital signals on Tuesday. We talked about how, you know, it's either a 1 or a 0, it's on or off. Technically, inside of the computer, right, that's actually a voltage. It's either a high voltage, if we were using the TTL logic that we talked about on Tuesday, you know, if it's 2 volts or above, it's considered a high or an on or a 1. And if it's less than 0.8 volts, it's considered a 0. All right. And so inside of a computer, in one location, right, in one location where you would have a value, that value can either be a high or a low. It can't be one of 10 different values. It can't be a 0, a 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10, or 9, excuse me. You know, it can't be any, you know, it's not like there's values between 0 and 9. You either have just a 0 or a high. And so computers, I don't care if it's your cell phone, your Fitbit watch, or your iPhone watch, or whatever, or it's just an ordinary laptop or desktop computer, or if it's a PLC. These are binary computers, which means that all they can do is sense that, yes, it's either a high voltage, or no, there's no voltage or very, very little voltage there, 0.5, 0.7 volts, right? So it's a low voltage. And that's all that they can sense. And so what we have to do, therefore, is do everything in binary. All right, so whatever a PLC does, whatever your phone does, whatever any digital computer does, it's always doing it in binary. All right, so as you go through these slides and stuff, we'll talk about octal number systems or hexadecimal numbering systems. But computers do not use those. They only use binary. That's the only thing that the computer can understand. So we need to be able to convert between the two and understand exactly what and how that PLC or that computer is understanding these numbers. All right, so and I just kind of mentioned we have an octal numbering system, which is base 8. We have a decimal numbering system, which is base 10. Hexadecimal, which is base 16. All right, and you can, if you don't like these, you could create your own. Let's say you want to create your own numbering system, base, 43 or something. You can do that. All right. I don't know why you would want to do that, but there's no law against that. You could create such a numbering system in there. And you can convert that numbering system between any of these other ones using what I'm going to show you here in a little bit. Now, the book also goes in, and these slides, at the end of these slides, they talk some about something called binary coded decimal. And I really don't like the way they give that the term that that's a numbering system. That's actually not true. It says it right here. It's coded. It's an encoding of decimal values 0 through 9. It's an encoding of the values 0 through 9 into 4 bits inside your computer, but it is not a true numbering system. Okay, so it's a little misleading there in some of that. So I just wanted to point that out at this point. But all right, so as I kind of mentioned about these subscripts here, right? We like to put subscripts when we're writing the number because it tells us what base it is. And that's all fine and dandy. The only thing is that when we are doing a lot of programming, we can't enter subscripts. Using something like PowerPoint that I'm using right now, or Microsoft Word, or some other fancy word editor, you can do subscripts and superscripts and all kinds of funky font stuff, right? But in basic programming tools like the PLC ladder logic, the Allen Bradley ladder logic, you can't put subscripts in there. All right, and so you can't put like a subscript base 10. So the one that we don't even have listed on this slide as I'm looking at this here, let me try and copy this and paste this. We don't have base 16 here. Let me just slide it in here. Let's say this one was base 16. All right. We don't have base 16. So what you'll find out is in a lot of programming languages, when you do these different, that's subscript there. Okay, and a lot of these programming languages where you like I say, like the Allen Bradley ladder logic, and you want to put in a base 16, what you would actually have to do is put in something like 173, and then they would either put an H after it, or some programming languages, they'll put a 0x there and then put the 173. So both of these notations would be for a hexadecimal number. And again, the reason that we do that is because you can't put subscripts inside of most of the programming languages. Even though it works great inside of PowerPoint or Microsoft Word, you can't do subscripts in all these various programming tools like the RS Logix 5000 or those sorts of things. And so when you see hexadecimal, a lot of times you will see either something written kind of like this with an H after it to indicate it's hexadecimal, or they put a leading 0 and then an X in front of it. Either one of those would indicate that it's a hexadecimal number as opposed to an ordinary decimal number. The octal numbering system, we don't see too much on, you're not going to see that on any modern PLC, but you may see that if you're still, a lot of companies are still running the old PLC5s or the Slick Logic PLCs, or some older PLCs that are maybe 15, 20, 25 years old. Those might use octal numbering in them. Okay, but the any of the newer ones, they'll either use decimal, binary, or hexadecimal. They won't use octal. All right, so when we talk about the different numbering systems, okay, binary means that we only have two choices. So binary has two symbols, 0 or 1, right? Octal means that we have 8, right? OCT is 8, like an octopus has 8 arms. We have 8 symbols. So what are those symbols? 0, 1, 2, 3, 4, 5, 6, and 7. Okay, 8 is not a valid octal number. Okay, so 1 0 in octal, 1 0 base 8 octal, let me put my 1 0 base 8 is the number 8 in decimal, or base 10. And so if we look at then base 16, which is hexadecimal, it has values 0 through 7, 8, and 9. But now we've ran out of numeric digits, right? Because we only have 10 in decimal, so we don't have any more symbols to represent those. So what they said is, let's use the first 6 letters of the alphabet to get those last 6 digits. So when we look at this then, if you look at in the octal, 7 is the last of the 8 possible values. If you look at decimal, right, 9 is the last of your 10 digits. So if you look at F, which is for base 16, it's 1 less than that. So F is actually equal to decimal 15. Okay, and so 1 0 base 16 is equal to 16 in decimal. Okay, so let me put this subscript on here. So 1 0 base 16 is equal to 16 in our normal everyday decimal or base 10 numbering system. Okay. So if we went back to my thing I said earlier where we were going to have a base 43 was, I don't know if I left that in there or whatever. I think I deleted it, but okay. So here, if we look at this for binary, okay, 1 0 in binary is the number 2. 1 0 in octal is the number 8. 1 0 in decimal, of course, is the number 10. Okay. 1 0 in base 16 is the number 16. And so if I was trying to do something like a base 43 that I mentioned earlier, okay, So base 43, 1 0 in base 43 would be 43 in decimal. Okay. Just to kind of give you an idea of, like I say, you can choose any numbering system you want in there. All right. So before we go into converting, the question kind of becomes, well, why, since we use the decimal numbering system and computers use nothing but binary, then why do we mess with something like octal or hexadecimal? Well, the reason for that is that if I wanted the number 173 base 8, okay, that is equal to 123 base 10. So I should have started there. So 123 base 10. So if we have the number 123, okay, that takes, to describe that in base 10, it takes 3 characters. To describe 123 in octal or base 8, we can still do that in 3 characters. But if I try to describe 123 base 10 in binary, I actually have to use at least 7 characters. Okay, so you see this, I've got 7 characters here, so I could leave off these leading zeros. I don't even know why they're on this slide. I could leave those off. But I have to use 7 characters to describe the number 123. So if I wanted to describe the number, say 1023, let's say I wanted to describe 1023, then I would have to use 10 digits. So I would have to have 10 ones and zeros all shoved together to describe the number 123. And that gets to become lots of ones and zeros. And when we look at all these ones and zeros, our eyes just start blurring and crossing, and we can't, it's really easy for us as humans to get confused and mess up when we're trying to like write down that number or add two numbers which are just ones and zeros all over the place. It's just really hard for us to keep track. And what we like about the octal numbering system is the octal numbering system, I'll show you this here in a little bit later, but I'll give you a hint now. Why we like this is I can take a binary number such as this one here, and I can write it as octal really, really, really easy. And I think that's why they actually had the leading zeros on there. Now I see that. So what we can do here is I can take this 3 represents these 3 bits. Let me change a color here or something. These 3 bits represent the 3 in the octal. And these 3 bits here represent the number 7 in octal. Okay, so 111 in binary, the 111 here in binary represents I don't know why it's not letting me highlight anymore. Click to let me just save this or something, because I just downloaded this and Maybe that's why it's not letting me save it. Okay, so, or let me change it or anything. So the 111 represents the 7 over here, and then the 1 represents, that's where the 2 zeros, that's why actually why they had those 2 zeros there. Okay. So and if we do hexadecimal, 4 bits will represent that. So I'll kind of show you that here later. My PowerPoint is not responding at the moment. So all right, so looks like I got it back now. All right, so but anyhow, again, why we like as humans to use either octal or hexadecimal. So octal, these three, the number 7 is represented directly by 3 bits, and the number 1 in octal is represented by 001. All right, so the 1 is represented, the 1 in octal represents 3 bits. That's actually why they had the 001 on there before. I wasn't thinking about that when I saw that, but that's why they wrote it that way, because it's a 1-to-1, it's a 1-to-3 relationship for octal to binary, and for hexadecimal, it's a 1-to-4 relationship. So if I wanted to write the number in hexadecimal, I would break it up, instead of breaking it up into 3 bits to make it octal, I would break it up into 4 bits. So let me just bring it down here, put it here, I guess. So we would take this number, I would break this number into 4 bits. Always start from the right side when you're doing that. So I turn this like green or whatever. So these 4 bits is let's see, 8 and 3 is 11. So 1 0 1. Let's see, the 9, I don't. Okay, 8 is 1000. 9 is 1001. A and B, so it would be a B. Okay, so if we were to write this in hexa, it would be a B, and then these 4 bits is a 7. So let me change the color on those here. All right, so it would be like 7B. Not sure what's, PowerPoint doesn't like me changing it while I'm sharing it with you or something here, but it would be a 7B there. There, I took it. Okay. So 7B in hex. Okay. And that's why we, as humans, like to use it, because looking at all these ones and zeros just get really confusing to us. But so by writing it as something more condensed like 7B or even 173 for octal, it's easier to see and understand. All right, so how do we convert between decimal and binary, or binary to decimal? All right, now what I'm going to show you here to do this conversion would work to go from decimal to hexadecimal, or from decimal to octal, but I would never do that because of this one-to-one relationship I was just talking about here. If you want to go to octal from binary or binary to octal, all you do is just grab 3 bits and match them up. Okay, and you know, each 3 bits. So start from the right, because here I had to add 2 extra leading zeros to match this one. Okay, and if you're doing hexadecimal, you match 4 bits. Okay, and the 7 here should be red. Let me change that red. Okay. All right, so to convert, what we basically do is we're going to break it down into the columns. So we're going to start out here with just decimal. Okay, so we're going to start out here with decimal, just to kind of remind you, this is the ones column here. This is the tens column, and the hundreds column, and the thousands, and the 10,000s, and whatever. So if we look at that using power notation, this is 1 times 10 to the power of 0. That's the ones column. This is 10 to the first power is tens, and 10 squared is the hundreds column, and 10 cubed is the thousands column. Okay, so that's for decimal. So if we do binary, we have 2 to the 0th power is a 1. This is always the ones column. I don't care which numbering system you're doing, even if you're using that 43 numbering system, you're going to have a ones column, right? And so it would be 2, well, this is binary, so it's 2 to the 0th. If I was actually doing a 43 base numbering system, would be 43 to the 0th power, and it would still be a ones column. So you have the ones column. But since we're doing binary here, the next column is 2 to the 1, so this is the twos column. And when we do the next one, this is the fours column, and the eights column, and the 16, and the 32. Now, when you work with these numbers long enough, you'll get used to this, and you don't even have to think about it too much. You can just say, you know, 1, 2, 4, 8, 16, 32, 64, 128. The next number, notice that basically we're doubling each number. So here it's base 2. So we always start out with the ones column. And so the next one is 2 times this column. 2 times 2 gives us 4. 2 times 4 gives us 8. 2 times 8 gives us 16. 2 times 16 gives us 32. 2 times 64 gives us, or 2 times 32 gives us 64. 2 times 64 gives us 128. 2 times 128 gives us 256, and so on. Okay, so all you're really doing, you can just kind of look at it as just saying, okay, I know I'm going to start out with ones. I'm in base 2, so I'm going to take ones, multiply it by 2, that'll give me a 2. Multiply 2 times 2, that'll give me 4. Now multiply 4 by 2, that gives me 8, and so on. All right, so even if you're, you know, I mean, if you have a calculator, you could punch it in the calculator, but you can also just kind of write it out on paper very easily. I was going to write it out on the board here, but the camera didn't seem to be picking it up too well, so. All right, so once we lay this out now, once we get this laid out like this, and we take a number, so in this case, I'm going to take the number 242 base 10. So this is the number 242 base 10 here. I should have had a base 10 there. And what I'm going to do is convert that to binary. Okay, and so to convert it to binary, I'm going to take, and since I'm doing base, I'm converting it to binary, which of course is base 2. I'm going to take this number and I'm going to write out this table like this. So we get 1, 2, 4, 8, 16, 32, 64, 128. So I'm going to write these out. Now, what I really need to do is I need to go to the next highest number. I didn't actually do that here, but I should have. So what I should do is I should have like go up one extra number. So that I told you, right, 128 times 2 is 256. All right, so you want this number here, your starting number should be bigger than this number. All right, and so this would be a 0 up here, because what we're going to do is we're going to start, and I'm going to take 256 minus 242. So 256 minus 242. Ask the question, if I subtract 242 off of 256, oops, I'm sorry, I did it backwards. 242 minus 256. So I'm going to subtract. I'm always subtracting the number in the bottom here. So I'm going to take my starting value, which is 242 minus 256. And I'm going to ask the question, you know, if I do this subtraction, do I get a negative number? Okay, so 242 minus 256 is going to give me a value of minus 14. Okay, so I would get a negative number if I tried to do that subtraction. So the point is that I'm not allowed to do that, so I'm going to put a 0 here saying no, you're not allowed to do that. Okay, so we put a 0 for the 256 value. Then, since I wasn't allowed to do the subtraction, I still have 242 left. So now I'm going to take the 242 and subtract the next choice, which was 128. And that I can do. I can subtract that, and I get a positive value when I do that, right? I end up with this positive value of 114. So I don't end up with a negative number. So I can do that. So therefore, I'm going to put a 1 here. So I'm going to put this 1 up here. But now I've got my remainder. My remainder is 114. Right, because I've taken away 128. I said, yeah, we're going to take that away. So I've taken away 128. So I'm left with 114. So I'm going to go over to the next column and look at 64. And I'm going to say, can I subtract 64 from 114 and keep the number positive? And the answer is yes. You end up with a positive 46. So that is allowed. So I'm going to put a 1 in the 64s column. Then I'm left with 46, right? That's what I got left is 46. So now I'm going to subtract the next column there, which was 32. So I'm going to subtract 32. And again, I'm going to ask, can I subtract 32 from my 46 and get a positive value? And the answer is yes, of course. The answer is 14. So it's positive. All right, so 46 minus 32 gives us a positive 14. And so I can do that. So I'll put a 1 here in the 32's column, and I have my remainder of 14. So now I'm going to take 14, and I'm going to subtract it from the next column, which is 16. 14 minus 16, that's going to give me a negative. Okay, oops. I'm sorry, it gives me a minus 2, so I'm not allowed to do this. Okay. All right, so 14 minus 16 is going to give me a minus 2. And I'm not allowed to do that, so I'm going to put a 0 up here. In the 16's column, I put the 0. So now I still have 14 left over, but I'm going to move to the next column. So I'm going to take 14 minus 8. Now that, of course, I can do and get a positive value. So I do that, and that gives me a, I'm allowed to do that because I end up with a positive value. So yes, that's acceptable. So I put a 1 in the 8's column, and I do the subtraction, 14 minus 8, and that leaves me with 6. Okay. And so then I have 6, and I'm going to go to the next column, which is the 4's column here. So 6 minus 4, and that, of course, gives me a positive 2 left over, so I can do that. So I put a 1 here, and that gives me a 1. Now that leaves me, that was the 4's column, so now I have 2 left over, right? I got a remainder of 2 here. I got 2 left over. So and I'm going to look at this column, and this is the 2's column. All right, and so I'm going to take 2 minus 2, and that doesn't go negative, right? It gives me no remainder, but it doesn't give me a negative value. Okay, so it gives me a 0. So I put a 1 here because I did that subtraction, and then I got nothing left. So I just put a 0 up here. And so 242 base 10 in binary turned out to be 1110, 1110, which is 8 bits. So again, remember this number here, which is only 3 characters, I now have to represent with at least 8 characters. But 110, 1110 in binary is the number 242 in decimal. And so if you were to type into your computer, like, and like right now, if I came in here, like in a calculator value, and I was to type into a calculator or whatever in the computer in the numeric field 242, it would actually be storing that like this. Okay, it would be storing 1110, 1110. And if it was a 32-bit storage location, it would put zeros out here, leading zeros to fill up the rest of the bits. But that is how we convert it. Now, I know that like took me half an hour to do, but it really, when you're just doing it, it actually works really easy, right? You're like, all you have to do is subtraction here, right? You just write out these numbers, and then you start subtracting. And so you take your number, whatever your number is, 242, subtract this value. Oh, I can't do that. I get negative. Not allowed negative. Subtract this value. Yeah, I can do that. And I end up with 114. All right. So we don't have to multiply or anything. It's all just done right there. Okay. So it's very easy. This there are a lot of different ways that they teach on how to do this. I find this way to be the simplest. If you have another way that you've been taught and it works for you, that's fine, as long as you're getting the right answer. It's perfectly fine. And you know, really, you can do it on scientific calculator, or you know, you can actually just punch in 242 and base 10 and tell it to convert to binary, and of course it will do that. That's fine, but you need to kind of understand what is going on here. You need to be able to look at a number sometimes and just have an understanding of least of what it is, and the fact that inside of the computer or the PLC, which is just a computer, it's storing number 242 as 11101110. That's how it's stored. All right, so now if we wanted to convert back the other way, what we do is we take this number and multiply it times this number. Okay, so in this example, I have an 8-bit number. So I have an 8-bit binary number, which is 10011100. And all you do is you have to just take the 1 times 128. Who can't do that? Okay, right? Any number times itself is just its number, right? So 1 times 128 is 128. 0 times 64 is 0. 32 times 0 is 0. 1 times 16 is 16, right? 1 times 8 is 8. 1 times 4 is 4. 0 times 2 is 0, and 1 times 1, of course, is 1. You add those all up, and you get back a decimal value. I should have base 10 here. This is actually base 10 down here. All right, but you just kind of add those all up, and you end up with the answer. And that's how you can convert between binary and decimal, or decimal back to binary, or decimal to binary. So is there any questions about that? Okay. Like I say, you may have been taught this a different method. I just find this to be the simplest method, but any method that you can do the conversion, that's perfectly acceptable as long as you're getting the right answer. Okay, so now when you're doing octal, as I stated before, octal, it's a 3-bit binary, 3 bits. When I say a bit, I guess I didn't really, I mentioned bit a couple of times. A bit is 1 digit in binary. It's either a high or low, 1 or 0, true or false. That's a bit. Okay, so this particular 1 or 0 here is considered a bit. And so to go from binary to octal, you could work through that same sort of method that I showed you to go from decimal to binary. You could go from decimal directly to octal, but I would never do that, because you just get used to doing the binary. You know the values of binary. And then all you got to do is take 3 numbers. So I have it over here for you. I actually have 4 bits in here, which is because I started out doing hexadecimal there. But here is your relationship between octal. This should actually say octal right now. Between octal and binary. Okay. Between octal and binary, you have a 1-to-1 relationship between 3 bits in binary to that 1 octal digit. So what we see here is when we look at this, it start from the right-hand side, 101, just come over here and find it. 101, that's the number 5. And then look at the next 3 bits. 011. Okay, 011, that's the number 3. And then look at the next 2 bits. Now, we actually only had 2 bits in here left, right? We had 1001, 1101. That's 8 bits. All right, so I used 3 bits here and 3 bits here. And so I only had 2 bits left. So I tag on an extra bit. So here's my 3 bits I'm looking for, 010. And I find that, and that's the number 2. So 235 base 8 is equivalent to this number in binary. If we want to do hexadecimal, then it's a 4-to-1 relationship. So 4 binary bits translate directly to 1 hexadecimal character. All right. And so we do the same thing, only we break it up by 4s. And again, always start from the right so that if you have an odd number here, notice that we should have 8 of these. Okay. So you take 4 of them starting from the right, and you find that 1101. Okay, where's 1101? That's a D. That's the letter D. And then look at the next one, 1001. That's the number 9. Okay, so the number 9 there. And so, and again, like either a 0x or a capital H at the end of it is often used to indicate that it's a hexadecimal value. Now, these 4 bits are referred to as a nibble. Okay, so any 4 bits grouped together is considered a nibble. And then if you take 8 bits are considered a byte. And I'm sure you're aware of, right, if you go out and you buy a phone or a memory for your computer or a hard drive or anything like that, a USB drive, right, any of these things, you know, when you buy them bytes at a time, right? They're usually nowadays it's like megabytes or normally more like gigabytes or even terabytes, right? But a byte is 8 bits, 8 binary 1s and 0s strung together as a group. Okay. A nibble is 4 bits. Let me add it to this list here, I guess. Okay, so a nibble is 4 bits. A byte is 8 bits. A word is 16 bits. Okay, a double word is 32 bits, okay, and a quad word would be 64 bits, although a lot of times, like if you're using a 64-bit computer, they may just call it a word even though it's actually 64 bits. Okay. But it's important that you know that a nibble is 4 bits, a byte is 8 bits, and a word is 16 bits. Because when we start looking inside the settings inside of our PLCs, okay, when we do a conversion of our analog signals that we talked about on Tuesday into a binary number inside the PLC, it stores them as a 16-bit word. So when you store that, it's actually storing it as a 16-bit word. All right, now if you go through these slides, I have a lot of different ways on doing conversions and stuff, so I'm not going to read every one of these slides to you. I do kind of want to show you this though. This is a timer, and I know in PLC1 we use some timers, but this particular timer here is actually a digital timer, and it's got little, these are called dip switches on here, and these are laid out just like we talked about with the binary. So these are seconds on here, and you flip these bits on. If they're on, then you know it's a 1. If it's off, you see the on and off over here on the right hand side. Looks like my mouse isn't pointing to that very well. Let me grab an arrow, see if that works. Okay, so you might see there's the on and off right over here. If you guys can see that. Yeah, the on and off switch is here. So when you turn these particular bits on, and if we looked at that, I don't know if I can zoom that up. Oh yeah, that looks like, right? So you can actually see up here the numbers: 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. So if I was, all of these are currently set to off. So if I was to flip the very last one on, then that would say it would be 512 seconds before this timer expired and turned on whatever it was that I was going to turn on. All right, so you know, this here refers to like the least significant bit and the most significant bit. And actually this, the way this is laid out, the most significant bit is on the right. But normally when we write numbers, the most significant bit is on the left-hand side, right? So like if we were to write in a number, you know, if I was just like to come up here or something and write in a number 1,478 or something, base 10, right? 1,000 is bigger than 8, okay? And so 1,000 is the most significant bit. So we typically put them on the left. It's just this timer example has them laid out the other way. All right, so, but here's a little bit of ladder logic with this timer wired in. So when somebody presses the switch, then that sets this timer, and the timer starts counting, and then after, you know, it hits that, then it would, you know, energize the relay or whatever. So that's kind of how that timer was used. All right, so again, a lot of these slides are just showing you some different techniques for doing the conversion of these methods. And again, like if you come in here, they're telling you to convert from decimal to hexadecimal. Honestly, I would never even do that. I think I just need to go in these slides and delete some of these things. I would not even bother doing that. As I said, when you do your conversion, go to binary. And then once you're in binary, go to hexadecimal or to octal if you have to do octal. All right. Now, the other thing, though, is let's say that you wanted to send a message from one computer to another. So you wanted to send some words. Okay. Remember, everything inside the computer is actually just a bunch of ones and zeros. So when we try to put in words, we had to come up with an encoding of those. So what they did was they started out in the early days, they created something called Ascii, which used 7 bits. Now remember, a byte is 8 bits, and memory inside of a computer is kept in terms of bytes. And so what they did was they said, we're going to use 7 bits, and then we're going to use the 8th bit as what they called a parity bit. It's kind of an error checking bit. All right. And so because back in the early days when they first tried to send data from one digital device to another, the the methods that they used to transmit the data was noisy and kind of unreliable. So they used that 8th bit as kind of an error checking bit that they called parity. And they would set it as either a 1 or a 0 depending on what type of parity that you were using. And then if it didn't match when it got to the other end, they would flag that there was an error transferring the data. All right, so the original Ascii chart, we had 7 bits, which meant that we could actually encode basically 128 items, okay, where one of those items was a 0, which was just a null. And when I say null, I don't mean the number 0, I mean a null. All right, so if you wanted to send, like, say, the letter A in capital letters here, you would send the bits right here. It's marked in this line here. You would send the bits 1 0 0 0 0 0 1, and then you'd send that that extra bit as a parity bit. So if you were doing, let's say you were doing odd parity, because you're going to send 8 bits. No matter what, you're sending 8 bits. And so the letter A has 2 1s. And 2 is an even number. 2 1s is an even number. So that 8th bit would be sent as a 0 if you were doing even parity. And so when you send those over, it's going to count how many 1s did I get. And it needs to know, the guy receiving the data, or the computer receiving the data needs to know that it was getting even parity. But nowadays, our methods of transferring data is so much more reliable. They don't do that. They do send error checking information now, but they send data, instead of sending data 1 bit at a time, we send it in huge blocks. And then we send what they call like a error checking number, kind of like the parity bit, but it's just a little more complex. So what they did was they said, you know what? We're going to extend this Ascii chart. Ascii, by the way, stands for American Standard, I forget the C, Code of Information Interchange or something like that. And so this was actually started out as an American code. And so, because it was created by, an American. I'm sure maybe other countries had created their own codes, but this code was created by Americans. And so the A stands for American Standard Code of Information Interchange. And but what they did was they said, you know what, the problem is with 7 bits, we can send, we can send the numbers, the digits 0 through 9. We can do some semicolons and things, and we can send like the letter, the alphabet. Notice we notice that here, what highlighted, underlined here is the capital letter A. Okay, so the capital letter A is 1 value, but a lowercase a, I guess it didn't make the chart. The chart kind of got cut off here. Okay, but a lowercase a is a different value. Okay, inside of this code. But what they did was they said, well, that works all great and fine, but when we try to like incorporate some other languages, like in German or Russian or something like that, we don't have enough characters, or even Greek, like the Greek characters like alpha and beta. We didn't have enough. So what they did was, after it got reliable enough, they said we can actually extend this and use all 8 bits in the code instead of sending the parity bit. And so by doing that, they were able to incorporate the Greek letters, all the Greek letters, and they were able, because you get another 128 possibilities. Okay, So with seven bits, you have 2 to the 7th possibilities, which means that you have 128 unique values, but one of those is all zeros. Okay? And so let me make this a subscript here. Or superscript, I mean. You have 2 to the 7th gives you 128 possibilities. But if we add one more bit, we can do 2 to the 8th. So one more bit will give us 2 to the 8th, which gives us 256. It doubles the amount of possibilities. Okay? And now we use what's called Unicode. If we have enough room, we have 16 bits, and we do Unicode, which means 2 to the 16th. Okay, so 2 to the 16th gives us 65,536 unique possibilities. Now remember, one of those is nothing but zeros, which is the null. But we still leaves us 65,535. This allows us to cover every symbol in every language on the planet and still have lots of space left over. Okay, so when we do Unicode, we got 65,536 unique possibilities of information that we can store in this Unicode value. And again, we can store like all the characters and you know, like the Russian characters, Cyrillic characters. We can store the Chinese characters, Japanese characters, and in their language. I've heard that like Chinese alone uses like 400 symbols. Okay, and obviously we couldn't have done that even with 8 bits. But once we went up to 16 bits, we can actually store, you know, all the possible Chinese different characters used in the Chinese language and every language on the planet. One thing extra I want to say about the Unicode is that the first 256 values is the extended ASCII code. So the first 128 values is the ASCII, the original ASCII code. And then the next 128 values are the extended ones that were added. So the first 256 values of the Unicode are the extended ASCII code. All right, so let me check here on the chat, see if there's any questions or anything. Okay, I don't see anything. All right, so let's do a little bit of addition then. So let's say that you wanted to take the values 5 plus 5 and you're going to add those together. Well, when you do that, remember that in decimal, we only have 10 possible values. And so what you have to do is you have to say, well, wait a minute. You know, 5 plus 4, of course, 5 plus 4 gives us 9. All right, and that's a valid, 9 is a valid symbol in the decimal numbering system. But when we try to add 5 plus 5, now we're out of symbols. We've used the last one with 5 plus 4. So when we try to add 5 plus 5, you know, we got to do something. So what do? Well, we put a 0 in the ones column and then put a 1 in the tens column. And so we have to do this carry. Now, we've been so long we don't think of it that way, right? But that's what we're doing, is we're doing a carry. We put the 0 in the ones column and carry to the next column over, which is the tens column. But in binary, you only have a 0 and a 1. And so in binary, when you're adding, you have 1 plus 0, of course, is just 1. But now when you try to do 1 plus 1, you're like, I'm not allowed to 2. The number 2 is not valid in the binary numbering system. So you got to do a 1 plus 1. You have to put a 0 in the ones column, and then you carry over and put a 1 into the twos column. And again, we don't think of it very much that way, but that's exactly how you add, right? When you're trying to count or whatever, you're adding 1 or 5 or whatever value you're adding, but you end up say, hey, I'm out of characters here, so I'm going to have to carry over into the next higher column. Now, this is really, really easy in binary to do. The circuit to do like 1 plus 1 and do the carry is actually very, very simple to build an electronic circuit to do that. And so they have adder circuits, right? You're actually in your computer, in the processor in your computer, it's got adder circuits to do this exact math. All right. Now, what about subtraction though? When you start doing subtraction, it gets a little more difficult, right? Because what you have to do here is, if you're saying, let's say I have the number 10 and I want to subtract 5. Well, 10 minus 5, okay, is going to end up giving us 5. But how do we do that? See, remember, it's been so long since we did that. What we would do is we would actually say, I'm going to have to borrow from the tens column. So that's going to give me a 10 plus the 0 minus the 5. All right. And I could do it better on the board. It's kind of hard to do it on PowerPoint here. But we're going to borrow. So let's say that you were doing something like 90 minus 5. Let's try something like that. So you're doing something like 90 minus 5. So what we're going to do is we're going to borrow 1 from the tens column, which would give us an 8. And then we're going to have the 10, because we don't have any in the ones column, but that would give us, 10 in the ones column now, right? And now when we subtract 5 from the ones column, when we subtract 5s from the one column, we can end up with 5 because we have 10 in there. And then that, of course, would give us the value of 85. All right, and so that's what I mean by borrowing. I think that maybe illustrates it a little bit better, right? So if we had 90 minus 5, we're going to borrow 1 from the tens column, which is 9 for 90. And that leaves us 8 in the tens column, but it gives us 10 in the ones column so that we can actually do the subtraction. And then we end up with our 85. All right, so this borrowing thing, okay, this is much harder to build inside of an electronic circuit. All right, they've built some, and it works okay maybe for 1 bit, but remember, like our modern computers are 64-bit computers. Okay, the PLCs are probably only 16, or maybe the newest ones are 32-bit, but you're like, even your cell phones are like 64-bit processors in there. And so think about, you would have to build a circuit to decide if you're going to borrow from the 64 column. And then you got to build another circuit to decide if you got to borrow from the 63 column. Then you got to build another one to decide if you're going to borrow from the, I lost count of where I'm at. And the circuitry gets really, really complicated because you had to keep track. Did I have to borrow from there or did I not? And So, you know, even a better example, maybe if I was subtracting 5 from this 900. Okay, let's look at this example once. I should have did that. All right, so we're trying to take 5, which is in the ones column, from the ones column, but there's nothing in the ones column. So I want to borrow from the tens column, but I can't do that because there's nothing in the tens column. So I first have to borrow from the nines column, right? So I borrow from the nines column, which gives me 1 in the tens column, or excuse me, I borrow 1 from the hundreds column. So that actually gives me 100 in the tens column, right? And so now I can borrow 1 from this one, which will give me 10 in the ones column, all right? So then I'm going to end up with 895 would be my result. But see, all this, I got to keep track of who I'm borrowing from and who didn't have anything to borrow from, and it gets, you know, and that was just with 3 characters. If you take this out to 64, it gets insane. Anybody ever try to subtract a 64-bit or a 64-digit value from, you know, from another value? It's crazy. So what some clever person discovered was that it's actually easier. Building adder circuits was really easy. They figured out even a 64-bit adder circuit is very simple to keep track of compared to the borrowing circuitry. And so, you know, if you try to borrow, it gets just so complicated. But somebody figured out that, hey, you know, really what we're doing is we're adding a negative number, right? So instead of, you know, if we're trying to take 5 away from 10, so 10 minus 5, what we're really doing is saying we're adding the negative value 5. So we're adding the negative value to the value 10. So we're doing addition, and we can build adder circuits. So if we do that, maybe it'll be a little bit easier. And it works okay if you do something called the ones complement. Now the ones complement means that you're going to flip the ones and zeros. Okay, so 10 in binary, remember 10 in binary is 10 10 in binary. So if you're going to flip that, you're going to get 0101. And 5 in binary is 0101, and you flip that and you get 1010. And that would be the ones complement. All right, and that's okay, but what somebody figured out was if you do something called the twos complement, if you do the twos complement and then add that, so to when you store the negative number, you make it what they call the twos complement. And then you can just add them together, and it just works out so nice. Okay, so what the twos complement is you do what I just did to create a ones complement. So you take all the ones in the binary value and turn them to zeros, and you take all the zeros and you turn them to ones. You just flip them. But then you add 1 to the result. And it turns out when you do this and you try to do the math, so in this case here I have the number 10, and I'm going to add 1 extra bit in here. So notice there's 1 extra bit. This extra bit is what we call the sign bit. Okay? So the bit, the most significant bit, MSB, most significant bit, is the bit at the left. Okay, and so it turns out that if you take and you use a sign bit, this is the sign bit. So we had the number 10, which took 4 bits in binary to get the number 10. And so we had to use 5 bits because we had the 5th bit is the sign bit. So to do this math, I just used 5 bits. But it turns out that, okay, these are positive numbers. This is positive 10. This is positive 5. A 0 for the sign bit, 0 means positive. And so this is positive 10 because it's got a 0 for the sign bit. This is positive 5. But now what I'm going to do is I actually want to subtract 5, but I don't want to build a subtractive circuit. So I'm going to negate the 5. So I'm going to do the ones complement. So I'm going to take all these ones and zeros for a positive 5, and I'm going to make them the opposite. So if it was a 1, it becomes a 0. If it's a 0, it becomes a 1. And that makes it the ones complement, right? So everything up here that was a 0 is now a 1. Everything that was a 1 is a 0. That's ones complement. Then I'm going to add one more. This is the twos complement. Now I'm going to take, so this is -5. This is -5 in twos complement form inside of my PLC or my computer. Now I'm going to add -5 to the number positive 10. So remember, this is positive 10, and this is my number -5, and I'm going to add positive 10 plus -5. And so what we have here, we're going to add each one of these. So a 1 and a 0 is a 1. A 1 and a 1 is a 0. Carry the 1. So I need to carry the 1. And then a 1, which I carried, plus a 0, plus another 0 is a 1. And then I have a, let's see, where was that? I have a 1 plus a 1. 1 plus a 1 is a 0. Carry the 1. So here's my carry. All right, but notice, so the carry is a 1, but I started out with 5 bits, and so I'm going to ignore this 5th bit. Okay, this one here, it's gone. I don't care about it. All right, and so your last bit that you carry over, even if it turns out to be a 1, we just ignore, and it turns out that this will always give us the correct value when we're adding these numbers. Okay, so I don't know who figured this out, but this twos complement is just awesome because we don't have to build really, really complicated subtraction circuits that decide whether we have to borrow or not. Okay, I don't know if you remember back in grade school when they were first teaching you how to borrow and you were trying to, subtract 25 from 100 or whatever, and you had to go through that whole borrow thing or whatever, and trying to build an electronic circuit to do that just drove people mad. And then somebody came and said, oh, make it a twos complement and just add it. And it's like, whoa. So it's just so nice. It works so well. So what we do then is anytime we store a negative number, we store it automatically as a twos complement. All right, so the number is automatically stored inside the computer as a twos complement. And then if you need to add, this number, you add it. If you actually want to do subtraction, you take the number, and before you do the subtraction, you apply a twos complement to it, which is going to turn it back into, you apply the twos complement to it. So like this, say here's the -5, and I want to subtract -5, okay? But I don't have the subtract circuit, I have to add it. So what I'm going to do is negate this. So this right here is -5, and I'm going to say I want to negate it. So I want to make it, you know, basically I'm going to flip the sign on it. So how do I do that? Well, we flip it. So it's 0, 0, 1, 0, 0. Okay, that is the ones complement of -5. Then I add one more to it to make it the twos complement. We add one more to it, which of course would give me 0, 0, 1, 0, 1, which was my original +5. Right? So if you negate the twos complement using a twos complement, you get back the positive value of that number. All right, so twos complement is, you know, if you're going to put a negative value inside of a computer, you're going to store it as a twos complement, and then you can do math on it very easily, because you just need an adder circuit to do, you never have to subtract. You just flip the ones and zeros, add one, and then add, okay? So you don't even subtract. It's really easy to build a circuit that can flip a 1 to a 0 and then add one more to that value. That circuit is just very simple to build, that electronic circuit. And so this is how they do it. So what you're going to see now is inside of our computer, when we have negative numbers, if they're going to have ones in here. So notice these ones here. Okay, the sign bit, a 1 means it's a negative number. But what you're going to notice is that, let's say that this is only 5 bits, right? This is 5-bit value of -5. Okay, that's what this number right here is. It's the twos complement stored, the value -5 stored in 5 bits. That's what we're looking at. So now I'm going to give it to you in 8 bits. So let's say we just had a full byte, 8 bits. Well, that would be 1, 1, 1, 1. I like to break them up so it's easier to see. 0, 1, 1. So if you wanted to store, this is -5 stored with 8 bits. And if you wanted to store it as a full word as 16 bits, it would be 1, 1, 1, 1, 1, 1, 1, 1. I'm going to run out of room here. And then the 8 bits that I just had. So it'll be 4 more ones, and then a 0, and then a 1, 1, 0, 1, 1. All right. So this is -5 for 5 bits. This is -5 for 8 bits, and this is -5 for 16 bits. Okay, and you can do the math. You can do it for 64 bits, and it's going to work out, and you're going to end up with, you know, if you try to add this -5, to add -5 to +10, you're going to end up with all zeros except the last, you know, the 1, 0, 1 at the very end. So if you, you know, but you would have to add the +10. So you would have to have, if you were doing 16 bits, you would have to add all the extra zeros in front of this to make it up 16 bits. And do the math and it will come out. All right, so that's twos complement. And again, the reason we need to know that is because that's how these negative values are stored inside of the computer.